Hello everyone and welcome back to Nunley Math as we enter into our second video in our series on radicals and radical expressions. Our previous video was a rather long introduction into some vocabulary and terms that we're going to be using. We talked about the fact that when you take the square root of radical expressions, there's a lot of different things that can happen. You can get solutions that are both real or unreal, and if you get a solution that's real, talked a little bit about how you can tell what type of a solution that will be, whether it will be rational or irrational. And then we also discussed the fact that sometimes when working with square roots, you're going to get multiple solutions. So if you have not watched that video already, I'm going to recommend you go back and take a look at that before looking into this video. So I do want to review as well before we begin some ideas that we picked up during our factoring unit. I'm going to walk through these fairly quickly because they are review topics for us, so they are going to be important today, but I'm going to operate under the assumption that you already know how to do much of this. I am going to suggest that when I put problems up on the screen, you pause the video, you try these problems on your own, and then you restart the video to see if your answers match what I'm getting. So I've got the trinomial x squared plus 2x minus 15. I'm assuming you've already paused the video and tried that on your own. I'm just going to remind you that when you're factoring a trinomial like this, we always look for a GCF first. This one happens to not have a GCF. And when we go to factor this, x squared can only be x and x. I look over here at this minus 15. The minus sign tells me that my signs are going to be different. So I need to find two numbers that multiply together to give me 15. 15 factors into a 5 and a 3 or a 1 and 15. So I'm going to plug those values in here, multiply these back together, and see which of those will give me the 2x in the middle. And of course, we end up with x plus 5 and x minus 3. If that seemed difficult or overwhelming to you, you probably need to go back and watch the video on factoring before watching this video. How about this one? 3x squared minus 15x minus 18. Again, you're pausing the video and you're trying that on your own. Make sure you take the time to look for the GCF first. A lot of people forget to take that GCF out. It makes the problem a whole lot harder. Once you've got the GCF out, you're going to factor this trinomial, realizing that there's only one way to get x squared. It's an x and an x. Realizing that since this is a minus 6, your signs are different. And then looking at factors of 6, either 2 and 3 or 6 and 1, plugging those in, guessing and checking until you get your minus 5 in the middle. And of course, you end up with 3 times x plus 1 times x minus 6. Here's one for you. When you look at this one, the first thing that I'm going to do is check for that GCF. This does not have a GCF. The second thing I'm going to do is check to see if it's a difference of squares. It is a binomial, so that certainly is a possibility. Notice that this is a perfect square, 3. This is a perfect square, x. And this is a perfect square, 5. As soon as I realize it's a difference of squares pattern, I instantly know what my solution is going to be. This one as well is a difference of squares pattern. Any even exponent is always a perfect square because when you multiply like bases, you end up adding the exponents together, which is always going to give you an even number when it's something times itself. 256 is also a perfect square. It is subtraction. It is a binomial. This is a difference of squares pattern, meaning that this is going to factor into this. Now, one very common error that a lot of my students will make is they will notice that this is an x squared plus 16 and x squared minus 16, but they may not realize that this is still a difference of squares pattern. Perfect square minus perfect square, this is going to factor again. This left side is not a difference of squares pattern. This is a sum of squares pattern. It does not factor. So this is your final factored form. Here's one for you. I'm assuming you've already paused the video, tried that on your own. I take out my GCF. Once I've taken out the GCF, I'm going to split this into two binomials. I'm looking for things that multiply together to give me 20x squared. It could have been 10 and 2 or 20 and 1, but through guessing and checking, I was able to come up with the solution you see here. Now that probably took you a little longer because I was able to guess and check off camera, so you have no idea how long that took me to come up with the right one. Last one here, this is a binomial. Notice that it does not have a GCF. The second thing I check for is a difference of squares pattern. This is not a difference of squares, this is a sum of squares. Sum of squares is not factorable. Okay, we're going to set that aside in our brain for just a second. We're going to revisit this in just a moment. I want to give you some examples of some patterns that might prove useful to us. Consider this. The square root of 36, we all know that that is a perfect square. It is 6 times 6. Remember that negative 6 times negative 6 also equals 36, but when we use this symbol, we're asking only for the positive root of. We discussed that in the previous video. But I want to do something else here. 36 can be broken down into the factors 9 and 4. 9 times 4 equals 36. But notice that like 36 is a perfect square, 9 is also a perfect square, and 4 is also a perfect square. Using order of operations, notice that if I wanted to simplify this, I would have to do the multiplication first, which would turn this back into radical 36, which we already know is 6. Look at this. I've got the exact same numbers, the 9 and the 4, but I've written them under their own radical signs. Notice the square root of 9 is 3, the square root of 4 is 2, and 3 times 2 is still a 6. In fact, this radical expression, and this radical expression all give us the exact same solution. They're all 6. I wonder if that holds for all radical expressions. Let's try another one. I know the square root of 225 is 15. Again, I just want the positive root of because I'm using this symbol. I can break that 225 into 9 times 25, or 25 times 9. That's 25, 50, 75, 100, 125, 150, 175, 200, and a ninth 25 would be 225. Using order of operations, this, if I wanted to simplify it, I would have to multiply together first and then square root. So this is also a 15. If I write them each under their own radical, the square root of 25 is 5, times the square root of 9 is 3, and 5 times 3 is 15. We now have two examples where we have 3 different ways to write the radical expression, all of which giving us the exact same simplified form. I'm going to do one more for you. The square root of 1600, well, I know the square root of 16 is 4, and when I square root, I cut the zeros in half, so 4 and 1 0 means this is 40. I also know that the square root of 16 times 100, if I wanted to simplify this, order of operations says multiply that together first, so that would turn back into 1600 square rooted, which is still 40. And if I were to write each factor under its own radical sign, the square root of 16 is 4, the square root of 100 is 10, 4 times 10 is 40. You have 3 examples where the square root of a number gave you the same value as if you took the square root of each of the factors and multiplied them together. In fact, that's a very important property that we have in this unit. It's called the product property for radicals. The square root of a number is equal to the product of the roots of its factors. That sounds really complicated, but it basically means this. If you have a number, in this case the number AB, you can split it up into its factors, like we did with the 1600 breaking to 16 times 100. We can split it into its factors, and we can take the square root of each of those factors separately, like the 16 and the 100, and we're going to get the exact same solution we got if we had just square rooted the number originally. Now, why is this important? Well, there is an argument that can be made for saying if this number is large and you don't know its square root, but you can split it into factors, you can make an argument that you could solve or factor larger numbers, simplify larger numbers by using the factors of the smaller pieces. Let me try that again. If you want to square root a large number and it's difficult for you, you could break it into its factors and square root the pieces instead, making it much, much easier. But that's not the primary reason we do this, because sometimes we're going to be asked to find the square root of numbers like 45. Up until now, if you got the square root of 45, you would look at this and say, oh, that is not a perfect square. That would come out as a non-ending, non-repeating decimal. That's going to be an irrational number, which would be true. The problem with doing this as an irrational number is that we have to use estimation in order to come up close to the actual solution. For example, I know the square root of 45 is between the square root of 36 and the square root of 49. The square root of 36 is 6, the square root of 49 is 7, and so you know this is going to be a decimal between 6 and 7. And in fact, in previous courses in my pre-algebra class, we would have talked about different methods for estimating what that would be as a decimal. The problem we have is it's always just an estimation. And anytime we use estimation or rounding, we make our answer slightly wrong. Ordinarily, in pre-algebra and below, that's not a big issue because we can talk about a number being close enough. But the higher into math you go, the longer and more complicated the problems get, and it becomes very difficult to have to either work with long series of decimals, or it becomes important to make sure that our solutions are as exact as possible. We don't like to round early on in long problems or large problems, because if you round early in the problem, everything you do after that magnifies that error. So we want to keep our answers in exact form as long as possible. So this creates an issue for us. The square root of 45 is going to be a decimal. What I'd like to be able to do is put it into a more useful form without having to put it into a decimal and round it off. And I'm going to use that property we learned on the previous page in order for us to do that. The property said that if I want to take the square root of a number, all I need to do is take the square root of its factors, and that will be the same thing. So I'm going to think about 45 and what the factors of 45 are. 45 is 1 times 45. It's 3 times 15, or it's 5 times 9. Those are the pairs of factors that would give me a 45. So if I want to put this radical into its most simplified or most useful form, what I'm going to do is I'm going to split it into a pair of factors that includes the largest possible perfect square. So I look up here and I say 1 times 45, those are not perfect squares, and that would, well, 1's a perfect square, I guess, but that wouldn't really make this any simpler. 3 and 15, neither of those are perfect squares. But when I get down to this 5 and this 9, I notice that 9 is a perfect square. In fact, it's the largest perfect square factor of 45. So I'm going to split this into a 9 times 5. Notice one of these is a perfect square, the 9, the other is not a perfect square. And then I'm going to split this into two separate problems, the square root of 9 and the square root of 5. Square root of 9, square root of 5. Because I am able to take the square root of 9, I already know that's a 3. I can't take the square root of 5, so I'm just going to leave it alone. I'm going to take the square root of the factor I can and leave the other one alone. The square root of 9 becomes 3. I leave the radical 5 alone. In simplified radical form, this is 3 times radical 5, and most of the time we don't bother writing that times symbol, and we make it 3 radical 5. Now, the idea here is extremely important and extremely valuable for us when we're trying to simplify large problems, because radical 45s are fairly rare. So the odds that you're going to find another radical 45 to combine this with are very small. But radical 5s are very easy to work with, and they come up all the time. By changing this from a radical 45 to a 3 radical 5, we've increased the likelihood that we're going to find something else that we can combine it with. That's the basic idea for today. I'm going to work you through several of these, and then some of them are going to get a little bit more complex. So make sure you watch all the way to the end. I will suggest that during each of these problems, you do pause the video. You try to find the solution on your own before watching me do it. If you get stuck, certainly just restart the video and you can watch along as I'm doing it. The square root of 75 is not a perfect square, so I'm going to look for the largest perfect square factor. So I think through this. 1 times 75, 2 doesn't work. 3 times 25, 4 doesn't work. 5 times 15. I'm going to go through there and I'm going to think about all the factors of 75, or all the factor pairs. Hopefully you've already realized that 25 is the largest perfect square factor. And you've already split that into 2 different square root problems. Notice I can take the square root of 25. I cannot take the square root of 3. So I get 5 radical 3. Not too bad, right? And usually we don't bother writing the time sign. Try that one. Radical 108. Hopefully you realize that the largest perfect square that can go into that is a 36. Which means I'm going to split this into a 36 and 3. I take the square root of 36 and get 6. And I just leave the 3 alone. Look, I got a little typo there. That's because I cut and pasted from over here, and I missed it. I'll go back and fix that. 6 radical 3. One thing to point out here is a lot of people get themselves in trouble because instead of using a 36, they use a 4 or a 9. Both of those are perfect squares, but they are not the largest perfect square that would go into this. You could do, I think it's 4 and 27 or 9 and 12, but that is not going to get it into the simplest form possible. Now, in another lesson, maybe we can take some time and talk about what to do if you accidentally use the 4 and the 9, because you would get an equivalent response that you could then break down a second time, but we're not going to get into that today. Here's one for you, 52t. You might be a little frustrated because we've not done one with variables yet, but just remember, times t is the same as times any other number. So when I look at this, I'm going to take that 52 and break it into a 4 and a 13, and I'm just going to keep that times t along the way. Because I can still split it into factors. The radical 4 still becomes a 2. I can't do anything with the 13. I can't do anything with the t. If I knew what number t was, I might be able to do something, but I don't know what it is, so I have to leave it alone. Last thing I'm going to do is go through and combine the things that are alike. That means anything that's outside the radical, I'm going to combine. It's just the 2. Anything that's still inside the radical, I'm just going to put back together. And you get 2 times radical 13t. Here's one. Again, pause the video. Try this on your own. I'm going to keep going. 49 is a perfect square, but x probably is not. I separate it into 2 problems. Square root the 49. I have to leave the x alone. And we get 7 radical x. This one's a fun problem. What's the largest perfect square inside of x to the 13? This is really interesting because a lot of people tell me that it is x to the 9th. But x to the 9th is not a perfect square. Remember, x to the 9th means that something times itself equals x to the 9. Well, you could do x to the 4 and x to the 4, but that's x to the 8. You could do x to the 5 and x to the 5, but that's x to the 10. You see, when we're dealing with exponents, we have to keep in mind that no matter what we multiply together, if I do x to the 1st and x to the 1st, I'm going to get x to the 2nd. If I do x to the 2nd times x to the 2nd, I'm going to get x to the 4th. Anytime I multiply a like base with the same exponent, I'm always going to get a result that has an even exponent. So every even exponent is a perfect square. That means the largest perfect square that's hiding inside of x to the 13th is x to the 12th. That's because x to the 6th times itself is x to the 12th. So when I split this and I say, what's the square root of x to the 12th? Well, that's x to the 6th. I can't do anything with the x to the 1st because it's not an even exponent. Your solution's x to the 6th radical x. Now, if we had more time, I would love to spend some time talking with you about the fact that we said the square root of a number is the same as x to the half. And we could talk about the fact that this is x to the 12th to the 1/2, and how the power of a power property says to multiply those together, and how that helps us define rational exponents. But again, that's not our focus here today. It's just one of those distractions that's very interesting to me and hopefully to you as well. It also helps show how we can tie things together from different units in our study. Last one of these, 80x to the 7th. Again, I'm going to deal with the 80 by splitting it into its factors. I'm going to deal with that x to the 7th by splitting it into factors. The 80 is 16 times 5. X to the 7, I'm going to plot the largest even I can. That's the x to the 6th, leaving me with 1 extra. 6 and 1 make 7. I'm then going to split it into separate radicals. I know the square root of 16 is 4. I know the square root of x to the 6th is x to the 3rd. And there again is another typo. Fix that, x to the 3rd. And when I put that back together, I get 4x to the 3rd radical 5x. Notice anything that was square rooted gets put together on the outside. Anything that was still under the radical gets put together on the inside. Not too bad, right? One more slide. I want to take this just a little bit, make it just a little bit more challenging here for you. The square root of 2x squared plus 20x plus 50. We can square root polynomials as well in some cases. The important thing to remember is we cannot square root individual pieces of a polynomial. As soon as we start sticking plus and minus signs into the problem, we have to be a whole lot more careful about order of operations. So we would not be able to square root these pieces separately. Instead, I need to think about what I can do to the entire polynomial. Well, probably now you've already realized this is the reason I had us look at factoring in our first slide, because I can rewrite this into factored form. I factor out the GCF and I look at what's left over. Notice that this is a perfect square, this is a perfect square, and this is 2 times the roots. This is a trinomial squares patterns. I like it when I get trinomial squares patterns because I can rewrite this as 2 times x plus 5 times x plus 5, or I can write this as 2 times this quantity x plus 5 squared. This squared right here is what I'm looking for because that makes this piece here a perfect square, meaning I can square root it. So I'm going to split this. The 2 I can't do anything with, but this factor right here is a perfect square. And we learned that squares and square roots undo each other. Now, I do want to talk about something here real quick. Notice, first of all, I use the commutative property to switch the order. You always want your numbers from outside the radical, the things you were able to take the square root of first, and the things that you could not take the square root of last. Otherwise, it gets confusing because people think this bar extends longer than it should and that sort of thing. This is considered the standard way to write it. The second thing I want to point out is we learned in the last video that squares and square roots do indeed undo each other, but what's on the outside is supposed to be in absolute value bars. Okay? It's supposed to be in absolute value bars. Now, we are not going to put them in absolute value bars for the rest of this unit. The reason for that is using absolute value bars is going to become a little overwhelming, and it's going to be a big distraction from what we are really focused on, which is the squaring and the square rooting. So just realize that anytime you have an x under a radical sign and you square and square root, it should come out in absolute value bars. But we are going to operate under the assumption for the rest of this unit that all of these are going to come out as positives. So you will not see me using absolute value bars for the rest of this unit, even though we said it is important in the last slide. Hopefully that made sense. One more for you. If you're fortunate enough and it is already written for you in factored form, notice that 4 is already a perfect square, but I have 11 of these. The largest perfect square is going to be the largest even number, which means I have a plus 5 to the 10th with the 1 left over. I'm going to square root each of those separately, the 4, the a plus 5 to the 10th, and the a plus 5 to the 1st. Square root of 4, of course, you know is 2. Square root of a plus 5 to the 10th, that is half times 10, or to the 5th, and then I can't do anything with this. Here's what that would look like, and usually we don't write the times signs. Be sure to keep the parentheses on this. A lot of students start to drop those parentheses, especially in an example like this one over here, where once it's outside, because the parentheses tells us that we have to do the addition before we multiply by the radical 2. That's all I have today. This is a little bit on the challenging side, so I'm going to give you several days of practice over the course of the next week or so if you're in my class to work on these and get better and better at them. If you're not in this class, just make sure you go ahead and check us out on our next video. Try to find opportunities to practice these on your own in between. Thank you so much for joining us here today. I do appreciate it. Hopefully you found this to be useful. If you have, make sure you smash that like button, turn on your notifications, and ring that bell so that you know what's coming out in algebra at Nunley Math. You guys take care of yourselves. Thank you so much, all right? Bye-bye.